In these videos, I'm going to be going through math, physics, and engineering practice problems. If you need help with any of your courses, or you want access to extra practice problems, check out my website linked below. In this video, we're going to take a look at the equations for a polytropic process and then solve a practice problem. But first, let's review the first law of thermodynamics. This is written as the change in internal energy is equal to the heat transfer minus the work. And the units for this are going to be joules or kilojoules. We can also write the same equation in terms of the specific internal energy, the specific heat transfer, and the specific work. The only difference here is that our units are now kilojoules per kilogram or kilojoules per mole. Let's take a look at our sign convention. Heat in is positive and heat out is negative. This is exactly the opposite of the work. A polytropic process is defined by this equation here. The pressure times the volume to the power of some number is the same for two states. Or sometimes they write PV to the power of n is a constant, and it means the same thing. We have a few equations for our PV-T relations. We can use these to solve for the pressure, volume, and temperature at each state. If we have the pressure as a function of the volume, we can integrate that to get our equation for the work done by a polytropic process. We'll skip the steps here and just use the result to solve our problem. The last equation that we have is our heat transfer for a polytropic process, where gamma is the Cp divided by the Cv of the gas. Now let's look at an example. We have 0.4 kilograms of a gas which is contained within a piston cylinder assembly. The gas undergoes a process which the pressure-volume relationship is PV to the power of 1.5, and that is equal to some constant. The initial pressure is 3 bar, the initial volume is 0.1 meters cubed, and the final volume is 0.2 meters cubed. The change in specific internal energy of the gas is negative 55 kilojoules per kilogram. There are no significant changes in kinetic or potential energy. Determine the net heat transfer for the process in kilojoules. First, let's write down what we were given and what we're being asked to find. We know that we have a polytropic process because PV to the power of some number is a constant. And we're looking for the heat transfer in kilojoules, so we're going to label that as capital Q. Let's start by using our PV-T relations to solve for the pressure at state 2. If we rearrange our equation and plug in our numbers, we'll get that the pressure at state 2 is 1.06 bar. Now we're going to need our pressures in kilopascals, so let's do that now. 1 bar is equal to 100 kilopascals, so pressure 1 is 300 kPa and pressure 2 is 106 kPa. Now we can calculate the work using the equation that we showed before. In this case, our N is 1.5, so if we plug that in along with our pressures and volumes, we get that the work is 17.6 kilojoules. We can use the work and the internal energy in the first law of thermodynamics to solve for the heat transfer. We just need to multiply the specific change in internal energy by the mass to convert it to the change in internal energy. Now that we have consistent units, we get that the heat transferred is negative 4.4 kilojoules. Since that's a negative number, we know that 4.4 kilojoules was transferred out of the gas during the process.